All right, so we look at calculating pH of weak acids. Now, as we know from the definition of a weak acid, it partially ionizes in water, or in short, it partially dissociates or decomposes in water. That means the concentration of the hydrogen ion is not the same as the acid itself in the beginning. And in this case, we are going to use what we call the ice tables. Now, what is going to help us calculate the pH of an acid at the equilibrium? It is the acid dissociation constant, the Ka, the one we calculated at first, right? For example, let's say I have an acid. Let's say now for a weak acid, we don't do the same procedure as a strong acid. A strong acid, just go direct and put pH is equal to negative log and so on. But for this one, you do certain things because not all the acid dissociates. So let's say we have a weak acid. Let's say we have a weak acid. This weak acid, we say, let's call it hydrogen fluoride solution of, let's give it a concentration of 1 molar. Let us also give it Ka of 7.2 times 10 to the power negative 4. So let's say this is an acid with that molarity this and the Ka this. How can we find the pH for this solution? Because the acid is weak, we first have to write the dissociation equation. So it's weak, so to have double arrow. So of course we're going to have our hydrogen ion. We're also going to have our fluoride ion. Now, ladies and gentlemen, when you reach at this stage, you go to the ice table. All right, ice table. I, the word I stands for initial. C stands for change in concentration. So this is initial concentration, change in concentration, and C is concentration at equilibrium. All right, so that's why we are using the ice table. So we do this. I, C. So what are, before I go there, let me do this. We have HF, then we have hydrogen ion. These are the ions these are the elements, or let's say the components of the solution that we have. Then we have these, right? Okay. Then we have I, like that. So the initial concentration of this one here is what? Is actually 1.00 molar, right? Yes. Were we given the initial concentration for this one? No, we are not given, so put 0. Even for this one, we do not have. What's the change in concentration? Now look, the reactants, they will always, as long as they are forming product, that means their concentration will always decrease. And because the products, they are being formed from a non-concentration, their concentration will always increase. So because this is a reactant, its concentration will always decrease because it's reacting to form product. So a decrease, we use negative, and increase, we use positive. So what I'm trying to say here is that we are going to let the change, all right, we are going to let the change in concentration, let's take it as x. Let the change in concentration be x. That means this will be 1 minus x. But for this one, it will be 0 plus x because it's increasing in concentration, because it's being formed. Even this one to be 0 plus x. That will be the change in concentration. Then we have what? Next we have the concentration at equilibrium. That means concentration at equilibrium for this one, it will just be x, 1 minus x. But for this one, it will be 0 plus x, just what? 0. 0 plus x, just be what? Be 0. Now, the change in concentration, ladies and gentlemen, it's not that much big. It's quite small that you can't even notice it. But nevertheless, we have to calculate it. Okay? So, like I said, the reason why they have given us Ka is to write that expression. If you remember, Ka in this case, because we've got these products, so we are going to have concentration of the hydrogen ion multiplied by the concentration of the fluoride ion over the concentration. Remember, we say the concentration for water, you ignore it. Concentration of the hydrogen fluoride. So this is at equilibrium, by the way. So Ka, we know it, right? Ka is 7.2 times 10, like that. We cannot directly find the pH. We need the actual concentration of the hydrogen ion at equilibrium. That's the X, which is here. All right, equal to concentration of this one at equilibrium is X. Even for this one, it's X. As you can see, X, right? And for this one, it's 1 minus X. Now, what can I say? You can solve this one using the quadratic formula, or this part here, the bottom. I'm writing here. The change is what? Is very small, such that we ignore it. What are we ignoring? The X at the bottom. If you want, you can go on. The answer that we're going to get, even when you ignore it, it won't be that much difference. So we have this X times X squared over, like I said, we ignore the X, just put 1 there. If you want, like I said, you can go on and start expanding until you go to the quadratic formula. You are still going to get the same answer even when you ignore it. Nevertheless, the difference, it will just maybe come 0.000 point something like that. That's why we just ignore it. It's negligible. So closing multiply, we get this 7.2 times 10 negative 4. So you do that, you do that. Of course, whenever you are solving a quadratic equation, you are going to get 2 answers, but we ignore the negative one. So our X, punching on the calculator, getting 2.7 times 10 to the power negative 2 as a value of X. Now, what is X indicating here? The concentration at equilibrium for both H plus and the F minus. And therefore, we can say the concentration of the hydrogen ion at equilibrium is 2.7 molar. Even the concentration of the fluoride ion is the same. But we need to find the concentration because we are only interested in the hydrogen ion to give us the pH. All right. So pH is there follow. All right. The pH is the pH is therefore equal to negative log then H plus. It should just be negative log. This one is 2.7 negative 2. So what do we get? Punch this on the calculator. You should be able to get this as a pH. That means you can also know the pOH, right? What would be the pOH? It would be 14 minus pH. Since pH plus pOH is equal to 14, you remember, right? So that means your pOH 14 minus 1.57. If I get my calculator and punch this, I'm getting 12.43 as my pOH and this one as my pH. It's simple as that. All right, thank you.